Came to Exeter as well. I'd be one of your lecturers in the first year. I teach vector mechanics and relativity, and straight after this I'm helping Hobbs' class for the first years downstairs. What I'm going to give you a little bit of a brief overview, because it's quite a big topic here at Exeter, is graphene. So we study it both experimentally down in the research labs, but also there's a lot of theoretical work on graphene as well. So I just want to give you a flavour of sorts of research we're doing here and why it's all interesting. So instead of giving you sort of lots of different applications where graphene could be used, I'll just give you a quick overview of what it is, of this material. So what we have is a single atomic layer of carbon atoms. And they're arranged in a hexagonal style lattice. So sort of hexagons with carbon atoms at each of these points. It's a single plane of atoms. So they're all bonded into these hexagons. The key thing here is that although it's one atom thick, it still conducts electricity. So the main reason that people got interested in graphene in the first place is it's the only material that conducts electricity on this sort of thickness scale. Why it's being thought of to be used in a lot of applications is the range of other properties that it has. And rather like this sheet of paper, if I look at this sheet of paper, okay, it's very thin, but if I try and pull this apart, it's got quite a bit of strength to it. And indeed, for graphene, even on atomic scale, it's still very strong. The interesting thing is, although it's strong, it's also extremely flexible. Again, rather like the paper, you can bend it, it curves. So, we've got strength and flexibility in the same material. We've also got the fact that it's transparent. If you hold it up to the light, I'll have to use an acetate rather than a sheet of paper, it is very easy to see through it. So it's practically transparent at all optical wavelengths. So why it's interesting for applications is that the combination of these properties give it a rather unique place in terms of materials and what you can do with it and what you can study in it. So in physics, for instance, we're trying to marry ideas of conduction through graphene with magnetic properties, with optical properties, with thermal properties. And it's all because of this combination of effects. And when you go downstairs, you'll see suites of instruments where we're trying to observe graphene and also turn it into useful devices. So when we initially worked on graphene many years ago, and we still use this technique somewhat, people have heard of this, this is how you create rather good crystals of graphene by exfoliating graphite. So you take a chunk of graphite, you take some sellotape or some sticky adhesive, you pull the layers of graphite apart, and graphite is just a stack of graphene layers. So you pull them apart, and if you put them onto a wafer, this is some silicon wafer, and look under an optical microscope, what you see is some sort of contrast on the surface. So these layers of material actually give you very good optical contrast. You can observe graphene, even though it's a single atomic layer, you can see it very clearly under an optical microscope. And that's because of interference effects that you're kind of used to. If you look at an oil slick on a road, for instance, the oil and water create some kind of interference effect, and that's where you get these different colours. So graphene is doing the same thing on this glass type surface. It's just changing the properties of light enough for it to be observed. So how do we actually make it in the first place? Okay, nature provides us with some graphene because we can get it from graphite blocks. But what about on a larger scale? Well, here at Exeter, we are growing it in various ways. One of our chief ways of growing it, and many other people around the world use this, is to grow it on some metal surface under high temperature conditions. If you put carbon into a furnace, you put some particular metals in that furnace, you can grow graphene on a metal surface. And this, well, it's a bit dirty and a bit dark here, this is the graphene on some silicon wafer. And what we do here at Exeter is we start to try and make electrical contacts to it. Here you can see gold contacts being made to a small portion of this piece of graphene here. There's also a more expensive way. This is silicon carbide wafer. And if you heat silicon carbide, you start to form graphene on the surface of the wafer. Once you create the graphene on the surface, you can make electrical contacts to it. Again, you can create graphene on wafer size objects rather than just have little pieces from a chunk of graphite crystal. You can also do it chemically. That's why it's interesting from a sort of general scientific perspective as well. There's uses of chemistry and physics and engineering in all of this. You can actually start off with some dispersion of graphene oxide. So this is graphene with lots of oxygen atoms attached to it. So each of these carbon atoms will have an oxygen attached to it. That's graphene oxide, and what you do in an experiment, you start to heat it up, those oxygens removed, and then you're left with graphene on the surface. And you can start to try and do this on a rather large scale. This was my postdoc here, and what he had done is he had created some graphene oxide, which is in a solution, put it on a large sheet of metal and tried to heat it up to try and reduce it to graphene. You can see there's some technical challenges in this. This is a 1 meter square sheet of metal. And he was trying to heat it with various little hot plates. And you can see that the heat is very localized here. It's very tricky to start building up onto larger and larger scales. Any sort of graphene layer tends to be very localized. So that was something my postdoc did. What we're tending to do with PhD students and master's students is to use these sorts of facilities you'll see downstairs to create graphene-based devices. So here is a suite of instruments that are designed to create some electronic device out of graphene. So when you want to look at the current through this device, you have to use various pieces of kit to take your raw graphene and turn it into some device for research. So you'll see those downstairs. And these are the typical devices we might measure. So you can see the graphene here. These are gold contacts connected to it. And you can imagine this is rather like a little resistor. You put current through two of these contacts and measure the voltage across. And you can do rather exotic things. This is a little golden bridge here. The graphene is in here somewhere and suspended. So it's a sheet of graphene held between 2 points, and then some golden bridge here to try and control its conductive properties. So rather advanced devices. What sort of things are we actually doing with it? Well, I've taken a sort of subset from what I've been doing in my research, which was starting to look at how electrons behave as particles and waves in graphene, so some quantum mechanical effects, and indeed there are some exotic properties there. This is all at very low temperature, so when you go downstairs you'll see a lot of instruments designed for low temperature research, down to a few millikelvin above absolute zero, so really quite cold conditions. We're also looking at heat flow in graphene, so graphene conducts electricity very well. It also conducts heat very well. So this was an experiment designed to look at what happens if you heat the graphene, where does the heat go? And it becomes a somewhat of a thermodynamic problem. You have various heat sources, heat sinks, and you can look at ways in which the heat is lost from this device. What you find is that graphene is extremely good thermally in terms of conduction, but very poor in terms of how much heat it can actually hold. It's only one layer of atoms. Of course, it can't hold a lot of heat, so if you put some power into it, it heats up very, very quickly. This was something my master's students did a couple of years ago in their project. So if you're doing or thinking about a master's degree, you'll be working for a couple of years in a research group. This was one of my master's projects, which was to look at what happens if you use graphene interfacing with some rather exotic optical structures. In this case, it was the surface of an insect wing, some beetle shell, which has a very exotic structure. It's almost like a little diffraction grating. What their master's students did was they interfaced graphene with that, and they looked at what happens if you start to heat the graphene up, put more and more heat into it. Well, this is some biological system. It's sort of proteins. What happens when you heat them? They contract or expand, depending on the temperature. If they contract or expand, that will change their optical properties. So their idea in their project was to take some graphene on top of a piece of beetle shell, like this, and to try and heat it up. They heat it up two ways. One, they heat it up just by increasing the temperature with a hot plate. And what you can see here, although I won't explain it in much detail, is that the wavelength they're observing, this is this axis, as a function of temperature. This is their maximum peak colour changed as the temperature increased. And you can see it up the top there in those little images. What's happening is as the heat is increasing, so the colour is changing from green to blue through to red. The idea was to create some sort of optical element, some colour element for a display. So that was their actual device that they made in the first or second year of their project, and they tried to put current through the graphene. So the graphene is holding heat, or carrying heat very well, and that changes only very slightly the wavelength in this case. This is the voltage they apply to the device, and they got a very small colour change. So they were working in the right direction. So you can see that the top image there is starting off very green. They start to get some bluish coloration coming in here as you heat it further and further. So that was a master's project. A year or so ago I had a Nuffield science student, A-level student, who came to me and to build something else related to heating graphene, which is if you heat the graphene, it doesn't hold heat very well, so it wants to get rid of it. So what happens is that the graphene, if you pump heat into it, it gets cold if you take that heat away. So if I put some current through, the bigger the current, the greater the heat. So this is temperature as a function of time, this is current as a function of time. You can see that when the current is large, the temperature is large. When the current is zero, the temperature is zero. So the graphene, as you pump current through it, is heating, cooling, heating, cooling, heating, cooling. And that's heating the air above it. So this was her device that she made over the summer. She heated it up, it heated the air above, and it heated it in little pulses, like this. These are heat pulses, so these are pressure pulses. So what it means is you can start to think about graphene used as a sound source. What is sound? It's just changes in pressure at different frequencies. So if you have a graphene device, and you put some current through it with a voltage source, and you pulse it, you can create sound out of this. So audible sound, you can hear it in the laboratory. What we've been doing over the last few months is to try and understand what is the physics behind this. How can we control it? So it's just about audible at the moment, but the graphene also heats extremely hot and to a very high temperature. What we're trying to do now is to understand what is the interplay between the heating and the current through the device. This is our setup. These are some microphones. This is this graphene device here. Some sort of meter separation between the two. And we're measuring with a microphone how loud the sound is from the graphene source as a function of the power and the frequency. To understand whether we can actually build also a speaker system out of the graphene itself. And so on. So there are many people in Exeter, both in physics, in biosciences now as well, and in engineering, looking at different aspects of using graphene. So I gave you an idea of what you could do in terms of the heat there, but others are looking at the optical properties and also its use in various sorts of systems. So in filters, in terahertz detection, and creating new types of material. This is graphene interspaced with iron chloride, and if you create this sort of material, it has also very unusual optical properties and conductive properties. So that was to give you a little bit of an overview of what we're doing here, and also the fact that master's students do get involved in this sort of research in their third and fourth years very strongly. So they're using all the facilities you'll see downstairs. They'll be within the research labs working on these sorts of projects. So I'll stop there.